Whoa. So I hope you guys are looking at your course there, seeing the cross section of the Earth. We're going to look at the core here in a few minutes, but let's take a quick look at this, the essence of geothermal energy. It's huge, man. Oh, he took a hit. Oh, he makes it. You know what I mean? Awesome. Super volcano, huh? That's I'm kind of a volcano freak. I really like volcanoes, and that was the trailer for the 2012 super volcano in Yellowstone. Shall we say a theatrical presentation? The possibility of what might happen. You can see we're back in the central core of your course here, topic 1. So hopefully you've looked at this already. Here's the core itself. Let's take a peek at this video here till we have a segue. Yeah. Okay, geothermal students, let's take a look now at the cross section of the Earth. Starting with the core, we'll work our way to the surface to see what the source of geothermal energy really is and where does it come from.
It was a secret government program known as Project Destiny.
We're building a weapon that could generate targeted seismic events.
Designed to use earthquakes to attack our enemies.
I'm getting a seismic reading.
It was a perfect, untraceable weapon.
Destiny is a go.
Until something went wrong.
That's an electrical superstorm.
Popping up all over the world.
I'll put this as simply as I can. Everybody on Earth is dead in a year.
The core of the Earth has stopped spinning.
The spinning core protects us from cosmic radiation.
Without it, radiation will create superstorms. Microwaves will literally cook our planet. How could this have happened?
It was Project Destiny. We killed the planet.
So, how do we fix it?
We can't. The core is the size of Mars. You're talking about jump-starting a planet.
What if we could?
We're here about your legendary ship.
What would it take to get it in 3 months?
$50 billion.
Will you take a check?
We need you to control the flow of information.
You want me to hack the planet? I'm gonna need Star Trek tapes and Hot Pockets.
You are good. Is there anything you can't do?
Not that I'm aware of.
You're trying to save the world. It's impossible. I came here to save my wife and children. I just hope I'm brave enough to save 3.
I can't wait to get into an untested ship, go to the center of the Earth, and restart its core with 1,000 megatons of nuclear weapons. Then we outrun the biggest shockwave in history.
Hot damn.
San Francisco is in ruins.
The whole West Coast is out. And it's decaying faster than we thought.
We're going in.
Whoever goes into the core is not coming back.
We're losing oxygen.
We got a job to do. Let's do it.
The core. There you have it, huh? Oh, sure.
It was a...
So here's where we can take a more, shall we say, academic look. Cross sections of the Earth. This is a great source of information. I'm not going to go into too much detail as far as sub-layers. If we take a look here at this Google page, cross sections of the Earth. Lithosphere, or the crust and uppermost solid mantle. But then you have, on top of that, you actually have a oceanic and a continental crust. So here you have a better look at it. By the way, the things that I emphasize in the lecture are going to be emphasized in the quizzes also. So there's a lot of information that we'll look at, but I will emphasize, to make it, shall we say, a little bit easier for you. I'll emphasize the areas that we're going to be concerned with. So here we have the oceanic crust, the continental crust. And the Morovic discontinuity is simply the interface here, the oceanic crust and the continental crust. And we're going to find out more about tectonic interfaces, subversive zones, submerging or subversive, transverse interface, and basically, is the rock going under or over? Is the oceanic crust coming up over the top, forming mountains? Continental crust is diving, which is usually the case, or is it out in the middle of the ocean where things are coming apart and they're actually forming a chasm or replenishing the Earth's surface? But the important thing here is you've got the lithosphere, first layer, the asthenosphere, right in here, and that all comprises the upper mantle. And then there's the lower mantle. This one's hard to see, it's kind of a small picture, but we've got the mantle divided into the upper and lower mantle. Then we get into the outer core. And it's this interface between the mantle and the outer core, this liquid interface that has a plasma element that we're going to look at. It's very important because the friction, the core of the Earth rotates the opposite direction of the mantle. So there's some friction involved there, but the plasma element, 4 states of matter, gas, liquid, solid, plasma. So we got that plasma element, very important. And then the inner core. I'd like you to take a look through here. This sums it up you know, as much detail as we really need here: the crust, the mantle, outer core, and the inner core. As far as depths are concerned, here you get into a lot of detail. The exosphere. This is the atmosphere is included, you know, as part of the sphere, which it is. And then the thermosphere, mesosphere, stratosphere, troposphere. So all very important parts, but now with geothermal, we're more concerned about the Earth, huh? So, but it is affected. It has a lot to do with, you know, purifying the atmosphere and, you know, creating rain, purifying the water cycle, evaporation and condensation cycles. We got the crust, upper mantle, outer core, inner core. Another way to look at it right here. This has a nice a quick reference for his, you know, about some approximate thicknesses. Crust is 0 to 100 kilometers thick. The mantle is from 100 to 2,900 kilometers, starting from the surface, correct? Then from 2,900 to 6,370, that's the core. And the core is comprised basically of iron and nickel. Mantle is mostly silicates, and the crust is mostly silicates. The actual mechanical aspect: lithosphere is rigid, asthenosphere is soft and plastic in general. It's pliable, moldable. The mesosphere is stiff plastic. The outer core is liquid. That's the interface between the stiff plastic and the liquid. That's the plasma interface. That at the time that they printed this up, they probably weren't aware of that. So that's something that's relatively new that we found out about. And it says basically the essence of cold fusion, which is a pretty big energy source based in geothermal. The inner core, solid. Well, we'll see more about that here. See just how solid it really is. Start to look at some of the mechanical interactions associated with the mantle, the crust, and the core. So the core is basically the fuel, and the mantle is basically the engine. Core is the fuel based in isotopic degradation, so it's isotopic breakdown. It's basically a big atomic reactor, and then that energy is transmitted through the core into the mantle at the plasma interface between the outer mantle and the inner core, the inner mantle and outer core. And that's where that plasma interface is so important, creating what we'll see is electromagnetic vortex, molten iron swirling like tornadoes, creating the magnetic flux, or the magnetosphere of the Earth, based in the convective cycles created in the mantle itself. Here you can see that core interface, about 4,000 degrees K, that plume of magma coming up in through the mantle, forming volcanoes at the surface. This is a replenishment in general of, and this is an oceanic, suboceanic crust right in here. That's where usually what we see the replenishment of the Earth's crust. And then it comes off in a cycle and then convects in a big rotary rotation, theoretically, huh? Here's where we're creating the counter rotation and the plasma element that then creates the vorticular or vortice generated magnetosphere. So don't worry about all that stuff. What's important is that it's hot down here. The hot wants to come to the outside. As it cools, it dives like you see here, and then recirculates, is re-melted by the Earth's central core. trying to say it's 4,500 Kelvin down there. Absolute. What's important is that you understand the convective cycles. Convective meaning hot air rises, or hot materials rise. As they cool, they tend to fall. And it's all, you know, in relation to the physics. As any material gains heat, it tends to have a larger, higher valence, or electrons tend to orbit in a larger, so we say the orbit pattern is bigger. So if you know your universe is larger, it takes more heat to maintain that. And as your items cool off, the orbits collapse towards the center or towards the nucleus of the atoms, and you get cooling. And of course, then the material gets denser. It's not as viscous. It won't flow like plastic. And that's why the crust is crusty. The oceanic plate, mid-oceanic rift, where we're replenishing the Earth's surface. And then as we get further into the course, we'll start to see how we get subductive plates, like you see here. The oceanic plates coming up against this. This might be the Marianas Trench, let's pretend. And there's the Himalayas, tallest mountains on Earth. And as that plate is subducted under the continental crust, you get this scraping, or like bulldozing. And that's what bulldozes up that suboceanic crust, forms and wrinkles up these mountains, forms these mountains. And then this goes down and replenishes, gets heated up and replenishes, and then as it's heated up again, once again, it'll come back up in a plume. And of course, this cycle here, we'll see that this cycle doesn't happen in a few years. It's a long-term cycle. The inner core, iron, solid iron is what they're saying, because of the pressures. It's all theoretical, but that's what the major theorists are propose now. And then speaking of Yellowstone, let's get back to the major. Yellowstone itself, see down here, that little snippet we just saw about. And I do hope that you'll take more time than this. At your leisure, please. Find the areas that interest you. Let's look at that lava plume here. Yellowstone caldera, the largest known plume of magma, rising basaltic magma. Yellowstone's hot spot under mantle magma and heat source. What's kind of cool is how, later we're going to study the footprints of this basaltic incursion from the craters of the moon all along the Snake River Rift. Snake River Rift is, a rift is a kind of a crack in the tectonic plates, and it's an interface where two plates are coming together, and it's most of the tectonic plates, especially the Ring of Fire, this is kind of a sub rift from the major Ring of Fire. This one runs basically west-northwest to east-southeast, and it's called the Snake River Rift. Whereas the other major rifts in the Ring of Fire basically run north and south. We'll look at that from Google Earth. There's some really cool stuff as far as the Ring of Fire, the Pacific Rim. But anyway, here's a proposed drawing. The granitic magma is partially melted, is coming up underneath the Yellowstone caldera, which, by the way, the Yellowstone, the volcano or the caldera, for years before they had satellites, the theorists, scientists theorized that all these different hotspots. You had geysers over here, mud pots over here. You had boiling river over here, and they thought, well, that's the center of the the Yellowstone Lake. That's the center of the volcano. That must be the volcano itself. Then they got up in outer space, looked back at the Earth from outer space, and they could see that there was areas. Ah, there it is. There's the ring. And in some places, the caldera is 275 miles across. So, but from space, it was obvious that there it is. So it's huge. And craters of the moon out in Idaho are previous examples of that, how that was working. But that's interesting. There's your academic look at the plume in Yellowstone. Getting to some of our temperatures. This is really fascinating when we get into our microseismicity later on, as far as determining where are geothermal sites and where do we drill. Where can we go to get the best energy? Thermal imaging is very important. See where there's just a little bit of detail, a few different viewpoints. We'll go into more detail later. What's important now is that you understand that there's convective cycles in the mantle that are driven by the core of the Earth, the isotopic degradation at the core of the Earth.